Okay, so welcome back. This is our sixth video about factor elimination and the Jointree algorithm. Let's start in talking about answering queries and setting evidence and see what message we have to redefine, recompute when we set the new piece of evidence. And let's think about a very simple case. We want to compute the marginal probability query on variables that appear together in a click, so we don't have any piece of evidence, anything. So let's suppose that we have something like, oh, we have a click that has A, B, C, and I want to compute like the probability of A or probability of AB or probability of AC or BC or something like this. So the only thing that I have to do is to take this guy here and eliminate the variable that I'm not interested, right? So I'm going to take this guy here and I'm going to be the phi something, like phi, and going to be the summation, and we take the variable C out of the phi thing that I have in this cluster here. So it's going to be very simple to do. A little bit more complicated that, okay, for instance, I want to compute a posterior marginal query. So I set some evidence E, and I have the query variables Q. And I have two situations. First one is that Q and E appear in the same cluster. That is going to be a little bit simpler. And in this case, just to be very clear, the union of the variables in the query and the variables in the evidence, they are a subset of the variables that have in some cluster CI. So I can just set the evidence in that cluster and sum out the relevant variables. So for instance, I want to compute something like this. Just erase this. So I have this cluster ABC, and I'm interested in computing like the probability of A and C. So little c here because C is going to be evidence. So what I have to do is, when I look at this cluster here, I'm going to see that is a table, and this table mentions variable A, variable B, and variable C, and it has a probability here. And if for the variable C, we'll have C in some rows and not C in the other rows. Let's suppose that's just binary. So the evidence is C true, so I will just eliminate everything that doesn't match the evidence, and I will eliminate the variable B because it's not part of my query. I will have the variable A together with C equal true. So this is the way that we do when the variables are together. In the last case, that's a little bit more complicated. The variables in Q do not appear in a cluster with E. So in this case here, for instance, we have this cluster, but I want to set like evidence, and it's going to be like D equal true, and D is another variable, but it's not occurring here in the cluster ABC. So what we do, we frequently use evidence indicators for doing that. So we create an evidence indicator for variable D, and we look for clusters. Here should be cluster. We look for clusters that mention variable D, and of course it doesn't need to be just one piece of evidence. It could have like evidence also for a variable E and some other variables that are not A, B, C. What we do, we go to the clusters that mention those variables, and we put the evidence indicator in those clusters. We multiply together, and we need to send the messages from the clusters where we put the evidence indicators, and we send the message from those clusters to the cluster that has the query variables. And when we get there, we sum out the variables that are relevant, and we give the answer. So this last case a little bit more complicated. Let's take a look in the next slide, one concrete example. So here we have one small example. We haven't used this example before in the previous video. In this case here, we're going to reuse those messages, and I want to compute this probability of C and little a. So little a is going to be our piece of evidence. And we need to select where we're going to compute this probability, and let's suppose that we decided to take from this cluster here, the cluster number 3. And it could use also the cluster number 2 if you want to, is another option. And let's suppose that this is the factor that we have here in cluster 1. So the first thing that we have to do is to introduce one evidence factor. So it's going to be the evidence factor lambda A, and it needs to go to one cluster that mentions A, and there is just one cluster that mentions A, that is this cluster here. So we're going to put together with this factor, we're going to put the evidence indicator, and I'm going to multiply those two things together. Let's take a look at the next slide. So here we have the evidence indicator. When we multiply these two things together, what is going to happen is that these two rows here that mentions not A and not A will have a value 0 here. So that is the way that we set evidence with evidence indicators. So when we have finished with that, if you have already computed those messages, we need to change some of them. So let's there are two different situations that can happen here. First is that we have not computed any messages yet. So what we do, we put the evidence there, we multiply, and we send the message as we did before, and we got the answer. But let's change this a little bit and think in a second case that's not uncommon. So frequently we have computed the messages, but we decided we're going to make a query, and that query involves one piece of evidence. So we need to integrate the piece of evidence and need to recompute some of the messages. So which message we have to recompute? So what we are changing is basically this guy here. So the big phi of this guy here, big phi 1 is changing. So yeah, if you change this guy, this message here is going to change. And this message here depends on this message here that we just changed it. So we need to change it too, right? And also this message here that depends on this message here, that is 2, 3, we're gonna need to change too. But if you look here on the other side, none of those messages depend on phi 1. So we have this message here that depends on phi 4, this one here mentions phi 3 and indirectly phi 4, and this one here mentions phi 2 and indirectly phi 3 and phi 4. So those messages here in the bottom part will not change. The only messages that will change are the messages that involve the factor phi 1 that we change it. So let's take a look at the next slide. Good. So this is a summary of what's going on. So we need to update this message here, and we need to update this message here. Just because we decided that we're going to compute the probability of P and little c from this node number 3, from this cluster number 3. Actually, this one is relevant. We can change it or not, but for the purpose of computing this query here, it will not change anything. And those messages that we have here in the bottom part do not need to change. So what we have to do is to change the message from the node that I changed, that I introduced the evidence indicators, and the message that leave this node here and go towards the node that I will provide the answer, that will compute the answer. These are the messages that need to be changed. The remaining ones do not have to change. Okay, so there are two main architectures for the Jointree algorithm, and those architectures, they basically change how we propagate the messages, how we're going to store those messages, how we're going to propagate them. So the architectures are called the Shenoy Schaffer and the Huygens architecture. So let's take a look on these two architectures. They will change a few details. The Shenoy Schaffer is slightly simpler, and it is more directly related to what we have discussed so far. And the Huygens is slightly different, is slightly more intricate, but it's also very interesting the way that they thought of this, how to build this architecture. So let's start with the Shenoy Schaffer, and then we move on to Hugin after we understand the first one. So this is the Shenoy Schaffer architecture, and it's basically the procedure that we have used so far. So it's very similar to what we have discussed. So let's take a look on this slide and just check if you have understood everything. So the first thing that we do, set evidence, entering into the Jointree the evidence indicators. So we just selected the clusters that mention the variable that we have evidence about, and we insert the evidence indicators in those clusters. A cluster is selected as a root, is a way to organize the message passing. We send the message into two phases: inward, that is towards the root; outward, that's away from the root. The inward phase is also known as collect or pull phase, and the outward phase is also known as distribute or push phase. That's good. And node I send the message to J only when it has received message from all the other neighbors K that are different from J. So how do we compute the messages? So we have seen these several times now. So the message from I to J is defined as, so we take all the variables that we have in cluster I, we remove the variables that are in the separator, and so we're going to do this summation here, and what's going to sum out? So we're going to sum out all the variables that are in the cluster but are not in the separator, and we multiply the bigify I, and the bigify I is defined as the multiplication of all factors associated with the node I, including the evidence indicator. So the evidence indicator, so it might be more than one. And so we take all those factors and multiply by all the message that we got from all the neighbors but J, right? So I'm going to send the message from I to J. So it's a message that comes from I, it goes to J. It doesn't include the message that we got from J, and that is very important. So we multiply all those messages together, and that's how we compute the message. At the end, when we got all the message passes, we went through the inward and the outward phases, we will compute the beliefs. So we have the probability for each of the clusters, and it will be the multiplication of the bigify I, all the factors associated with the node I, together with all the message that we got from all the neighbors, right? So that there is no exception. There is one exception here, that we don't include the message from J when we send the message to J, but once we have sent all the messages and received it, and we need to compute the beliefs, what's going to be the marginals in each cluster, we multiply the factors by all the incoming message that we got from all the neighbors, and went to the node I, and we have this. So once we have those marginals in each cluster, we can answer queries that mention the variables in the cluster. So in this case, we just take a subset of those variables. We eliminated the variables that we are not interested in and return the answer to the user. Okay, one interesting aspect of the Shenoy Schaffer architecture is how it stores the messages. And it's interesting to note that only the messages are stored. So the Shenoy Schaffer architecture, it reserves one factor. So I'm going to store one factor for each message, and we have two messages per edge. So I'm going to have one here and one here. So actually this is 3, 1 and not 1, 3. So it's going from 3 to 1. And so when we start, let's suppose that the first one that the first node that I send a message is the node 1, so I send the message to node 3. I fill in this factor here with the information of the message from 1 to 3. So if it sounds strange to you to say that message is a factor, it is. It's just a multiplication of the factors and elimination of variables. It's going to be a factor at the end. So a message is a factor. And let's suppose that after that we go to node 5 and decide to send a message 5 to 3. So I'm going to have another factor here that I'm going to fill in with the information and send this to node 3. So when 3 has these two messages, the message from 1 and the message from 5, it will be in position to send a message to 4, right? So it's interesting to note that the Shenoy shafter does not store anything in the cluster. It just stores the factor that we have before, but it doesn't store any computations. So here we'll have just the factor, the big phi 3, right? That's the multiplication of the factors that I put here with the evidence indicators. I will take this phi 3 and I will multiply the message from 5 and the message from 1, and I will eliminate the variables that are not in the separator. In this case here, the separator is AF. I will eliminate the variable D that I have here, right? So that will occur for every message that I want to compute, because I'm not storing any computation in the nodes here. Every time that I need to send a message, I will take all the incoming message that I got, I will multiply by the factors that I have stored in my node, and I will eliminate the variables that do not belong to the separator. I will push this message to my neighbor, and I continue to do that, right? So what is good about the Shenoy shafter? The Shenoy shafter is interesting because in terms of space, it will only store the factors over the separators, and typically the separators are smaller than the clusters. So we can see here that we have separators over 2 variables and the clusters are over 3 variables, so we can save a little bit of space. Usually the separators are smaller than the clusters. But the Shenoy shafter is a little bit expensive in terms of time, because as it's not storing anything in the clusters and recomputing the messages from scratch every time that we need to send a new message, I will multiply again all the messages I got from all the neighbors again to compute the message I'm going to send to you. And if I have another neighbor, I will multiply all the neighbors that I have together, not including the other neighbor, in order to send the message to the other neighbors, and keep doing this all the time. So it's a little bit expensive, because if you have nodes that have a bunch of neighbors, every time that I need to send one message to one of those neighbors, I need to multiply everything together with my factors, all the messages, and send the message to the neighbor. So Shenoy shafter is simple in terms of implementation. It is good in terms of space, but it tends to be a little bit time consuming for computing all those messages over and over again. Okay, so we can now discuss the Huygens architecture, and the initial steps that I have here on the left are the same ones that we discussed for the Shenoy shafter architecture, so I will not cover these again. Let's just discuss this part here on the right. There are the difference between the Huygens and the Shenoy shafter architecture. So the main difference between Huygens and Shenoy shafter is the fact that the Huygens architecture does store multiplication of factors and messages in the clusters, and that is something that is good and bad at the same time. The first thing is bad because the clusters tend to be larger than the separators, so we will spend more memory in the Huygens architecture than the memory that we spend in the Shenoy shafter architecture. But we can also speed up things a little bit using this technique, but we need to be a little bit careful. So what's going on is that in the clusters we'll have the factors, the evidence indicators, everything multiplied, and also the messages. But we need to be careful, because when I want to send the message to you, I need to discount the message I got from you. So if we multiply everything together, I have to find a way to remove the information of the message that I got from you before I send a message to you. And the way that's done in the Huygens architecture is by a factor division. So if everything is put together using multiplications and I want to remove something, the way to remove is to divide by the message that I got from you. So there are a few differences between Huygens and Shenoy-Schaffer. Let's discuss this by following this slide. So it says that each separator xij has a single factor psi-ij. And this factor, it is each entry is initialized with a value 1. So this is one first difference. The Shenoy-Schaffer architecture has two factors per edge, so it will have two factors per separator, and here we have just one. Each cluster Ci has a factor psi-i, and this factor psi-i, it's initialized with the big phi I, that is the multiplication of the factors and the evidence indicators, together with the message that we got, the psi ij. There are the factors associated with each separator that are initially all 1, so we will not change anything here. When the node I is ready to send a message to a node j, the node I does the following. So these are, just to clarify here, these are the steps that are done by the node I, and these ones actually done by the node j. So the node I saves the factor psi ij into psi ij old. Okay, it computes a new factor psi ij that is the psi I with the elimination of the variables that do not belong to the separator. Okay, it does make sense, but again, we need to be a little bit careful, because this psi ij is removing the variables, but we are not removing the message that we got from j that might be stored in this psi I factor here. So it will be important to remove this. And the way that is done is the division in the next step. So it computes the message. So we see that the psi ij is not a message actually. The message is computed from the psi ij, and the message from I to j is going to be the psi ij divided by the psi ij old. Okay, that's interesting, but not totally trivial. And when the node j receives the message, it basically takes that message and multiplies by, actually there is a mistake here, by the psi I, not psi ij. So it basically is incorporating the message into the factor psi I that is stored in the cluster I. So it will be part of the factor that is stored in the cluster. So let's take a look at the next slide in order to clarify a few details. So the Huygens architecture will store one factor for each cluster and one factor for each separator. So we can imagine that we'll have like one factor here that is reserved to store. It's going to be over the variables f, d, g over there. There will be just one factor here that's going to be smaller, just over variables d and f. There will be a larger one here for a, d, f. There will be a smaller one here for the separator AD, a little larger one here for ABC, and so on. So we have all those space, and initially the message is for the factors for the clusters are initialized with the factors that we received from the graphical model multiplied by the evidence indicators, and these other factors here are just initialized with values 1. So yeah, it will not change anything here. And let's think about what's going on when we are sending messages. Let's suppose that 4 is ready to send the message to 3. So, but it has not yet received the message from 3. So that is going to happen, right? So we have messages in both directions. So you need to send one message in one direction first, and we'll have the message in the other direction that's going to occur later. So let's suppose in this example that this message here is going to happen first. And so 4 received the message from its neighbors, it's all fine, and now it's ready to send the message to node 3. So when it does this, what happens? It will take everything that it has stored here in its factor. It will remove the variables that are not in the separator. That's all fine. And it will divide it by 1. And the division by 1 will change nothing. Right? So the message is basically whatever it had here in the cluster with the elimination of the variables that are not in the separator. And that's fine because we do not need to discount anything because 4 has not yet received the message from 3. So there is nothing to take out. But in the process of sending the message, it will erase this guy here, that's 1, and we will replace this guy by another thing. So this guy here that used to be 1 is going to be now the following thing. It's going to be the big psi ij is going to be the sum. I'm going to take all the variables in the cluster but the ones in the separator, and this from the psi I. So what's going on here is that I'm going to store here this guy, the result of this equation here, that is the elimination of every variable that does not belong to the separator that have here. And that is actually the message, right? Because it does not incorporate the message that went from 3 to 4. It's the same thing as the message. The message is computed from here by doing a division by the psi ij old that was basically 1. So this is actually the message for this case here. And okay, so 3 now, let's forget about 4. 3 received this message. It will take the message and multiply in this factor. Now the factor has this information. It will receive the message from 1 here, and it will multiply here. It will receive a message from 5 here. It will multiply here. I will not actually update this, but it will be updated, but I will not discuss this now. So the factor of the node 3 will have all this information. So it will have the initial phi 3 and multiply it by the message that we got 1 3. We also got a message 5 3. We also got the message 4 3. And now, because we received the messages from 5 and from 1, we are in the position of sending the message to 4. And that is a problem because we want to compute that message from this guy here, but it does include this message here that came from 4. But well, we have this information here on the top that was the message that I caught from 4. So what I'm going to do, I'm going to divide it by this quantity here. So it's going to be a factor division, and the factor division is basically the same thing that we did with factor multiplication, but instead of multiplying, of course, I'm going to divide, but it is a sequence of divisions of real numbers, right? So we can think that we're going to make a division for each entry in the factor according to the values of the variable. So the values of the variables needed to be compatible. But yeah, basically it's the same implementation of the join, but now with a division instead of a multiplication. There is one problem, is that when we receive a message with zeros from the other side, and when we multiply this, it's all fine. Multiply 0 by something, it's going to be 0. But when I'm going to divide it back, well, we're going to be division by 0, but we just assume that we got the 0, and we're going to send again the 0, so we will define this division by 0 as 0, and we solve the problem that way. So when we send this message here, what we do, we take this guy, this one here, that is the information that we have in a cluster, and we divide it by this information that we have here, and we rename this with old and divide it later, and we'll have the right thing to send it back to 4. And that is the general idea. So why we are doing this, and basically we are doing this to save time, right? Because when we have the Shanoy Shafter architecture, every time that we wanted to send a message, we did the same operations again. We multiply the factors by all the incoming messages and send the message to the other one. But now we don't need to do this because we have already the incoming message multiplied by the factor is stored in the node. The only thing that we need to do is one division, one factor division by to discount the message that we got from the node that we are sending the message now. So we're going to save time, but we're going to spend more memory in order to store the factors in the clusters. So that is the general idea. Of course, there are minor technical details here and there, and you can double check your understanding by going through the lectures again and also taking a look at the textbook. So great, we got to the end of our lecture. We have discussed the factor elimination. It is a sort of an alternative view for variable elimination. Both techniques, they decompose a graph by eliminating or one factor at a time or one variable at a time. And there are connections between these two things that I'm going to explore in the next lecture. The key idea here is that we can use message passing formulation in order to save computations. And you're going to save those computations into a Jointree. So the Jointree is a probabilistic graphical model that is used to make an inference. So it's different from the ones that we haven't seen before. Most of the graphical models that we have seen were about modeling, but this one, the Jointree, they are not good to model anything, but they are very good to answer the query. So they're going to store the partial computations into the Jointree and use the Jointree to answer multiple queries, and you're going to save time because the complexity of the Jointree to answer multiple queries is the same as the complexity of the variable elimination to answer just one query. So another thing that's important is the fact that this idea of message passing will be used as a base for some approximate algorithms called the belief propagation. So in this case, we will transform our Jointree into a join graph. So we will have cycles, and we will be into some issues because we saw that to start sending the message, we needed to have one node that was one peripheral node. But now if we have cycles, we will have this dependency. In order for me to send a node to you, I need to wait for someone else, but we are in the cycle, and how to solve that. And the belief propagation will solve this issue using an approximated inference method. So I invite you to check chapter 7 from the textbook in order to see more details about those algorithms, and we will continue in the next video now discussing the relationships between the techniques that we have seen so far for doing inference in probabilistic graphical models. So see you soon.